Welcome, everyone. Good morning, good afternoon. Welcome to the Densify webinar of the day, Realistic Strategies for FinOps-Driven Kubernetes Optimization. I'm here with Andrew Hillier, our Chief Technology Officer, and we're excited today to talk to you all about this topic, kind of inspired by numerous conversations that we had at FinOps X a couple of months ago, where there was a lot of interest in addressing the more complicated world of Kubernetes and containers as it relates to optimization of cloud cost and its overall component as part of a FinOps strategy. As containers and Kubernetes become more common, this is a growing concern. So Andrew, let's jump into it. Densify is an analytics engine precisely and purely focused on the challenge of optimizing resources for both cloud and increasingly containers and Kubernetes infrastructure. We do that across all the major platforms and Kubernetes generally wherever it is found. So over to you, Andrew.
Thanks, Chuck, and thanks everyone for joining. Today's topic is on the Kubernetes icon on the right-hand side and FinOps. I'm going to try and stick very closely to that topic. And one of the points I'll make before going off this slide is that I think FinOps in a Kubernetes environment, it does look a bit different than in the cloud environments on the left. I'll try and explain that to a certain degree. It's all the same goals, but the tactics and methods tend to look a bit different because of the complexity of Kubernetes. And that's what I'll try and capture as we go through this. And to that point, we always like to start with the top challenges in FinOps. And there's a great list. Of course, number one is reducing waste of unused resources. That is the real focus, a big focus in Kubernetes as it is in the cloud. But again, it tends to look a little bit different than the other things. And the other thing I'll note about this list, and I'm going to do a walk down memory lane in a second. None of this stuff is really geared towards making sure there's enough capacity. It's all about making sure there's not too much and making sure there's accountability and reporting and all these things. And that's the interesting thing about FinOps. And if we look at why that is, and kind of what I would call the evolution of saving money, and I have enough gray hair to be able to go back in time and talk about it historically, about the methods have been used and how we've evolved. So if we rewind, it's not even rewinding, everybody still has VMware, but in a kind of a legacy environment, there used to be capacity management teams, and there still are. And the focus of capacity management is making sure there's enough capacity without having too much capacity. And that's a nice, simple way to put it. So when there's a capacity management team at play, this is kind of a combined function. They're responsible for making sure that they have enough capacity on the floor to meet the application demands as they come in the long term, because it's a long lead time to buy on-prem, but also not too much. So again, we've worked extensively with capacity management teams and in all kinds of ways to make sure you're getting the right amount and not too much, so you have efficient procurement and you don't have any capacity risk. And the interesting thing about that is also in these groups, sometimes we would see them approach app teams and say, well, you should make your VMs smaller because they're all too big. But the neat thing about VMware is you don't really need to do that because there's overcommit. If you get them all wrong in the VMware environment, if everybody's asking for 8-way VMs, you just overcommit. Essentially, the platform team can turn up the overcommit and you can get efficiency again. And that's exactly what we saw. It's one of the big powerful features of technologies like VMware is that you can overcommit. So we didn't see a lot of capacity management approaching app teams. We saw some, but generally you could just overcommit your way out of it and get to an efficient state. Now, let's fast forward to public cloud. And in public cloud, because the resources are on demand, and this might be a statement of the obvious to a lot of people on this call, the app teams themselves can be responsible for having enough capacity. I don't need someone to buy it months and months ahead. I can just turn it on with a credit card. I can make scale groups that go up and down dynamically. And that's really obviously one of the big powerful aspects of public cloud is the as a service on demand. But of course, in the early days, that generated a lot of waste. So, enter FinOps, which really has the financial oversight function. So it's in many ways, if you compare it to a capacity management, it's like a split function now. We have one team that's making sure there's not too much. Of course, they want to make sure there's enough, but it's not already in the purview of FinOps to understand the apps to that level to say there's enough. That's the responsibility of the app teams. And create a dynamic, which we all know and love, where there's a lot of recommendations being passed saying, hey, you should make that thing smaller, that R6i extra large should be a large, or you should turn that off. And of course, there's buying savings plans, that type of stuff. But there's a flow of recommendations. And that survey I showed in the previous slide really was geared, a lot of it was geared towards this, making sure the engineers are empowered to optimize, but it's really a decoupled role. And again, I live and breathe this every day with our customers. And it's all about accurate recommendations and confidence and the evidence to make sure that people can take that action, opening change tickets, that type of thing. So that's kind of the public cloud dynamic when it comes to optimizing. Now, Kubernetes is a lot more complicated. It's not just I've got an R6i extra large, make it a large, and then they say, nope, needs to be like extra large, or yep, that looks good. It's much more complicated. And there's a lot of layers in here, and they all have to be looked at once. So I can't just say, oh, go downsize the nodes, or oh, go downsize the containers, and we're good. We're done. It can be done, but it's just, there's some nuances to it that I'll cover. So in this, it's very much interlinked, even more so than VMware, because VMware, your VM was a hard boundary. Nobody else can mess with you. You got your 4 CPUs, but in containers, everybody's swimming in the same pool. So you need to make sure they're big enough, but not too big. And then you got to understand how that's affecting the scaling, the scale groups, all that type of stuff. And again, so it's not as simple. There's a lot of savings to be had in every environment we see, but you need to unpack this a bit to understand it. And the key things in this is that where the cost is incurred, where you'll see it on the bill, is the scale groups or the instances or the bare metal that you purchase if it's on-prem. Everything I'm talking about applies to both on-prem and in the cloud. I'll talk a little bit about both. So if I'm buying scale groups, that's what shows up on the bill. I just see a really big scale group, really expensive. Wow, these containers are expensive. But again, I can't go and just directly downsize those things because they're being driven by this stuff. So not just utilization, but the actual requests. When app teams ask for resources, that needs to be fulfilled in the infrastructure. And then there's all kinds of complexity in between there that comes into play. So there's a ton of moving parts where all this is interacting. And there's usually a lot of savings, like a ton of savings, but you have to be smart around how you target this stuff. Some things you do might have no effect. Some might have a huge effect. Some might have an adverse effect. And I'll cover a bit of that. So you can't just go guns a-blazing in here and start downsizing things. It's a little more nuanced than that. In that sense, the topic of the webinar was reducing node counts. Also, not just reducing node counts, but actually changing the nodes, gaining efficiency. We'll be talking about that. And also specific, not necessarily in this order, reducing the CPU waste that's out there and reducing the memory waste. And they're two different topics, and I'll explain why, because you have to approach them slightly differently. We analyze a lot of environments. We have a lot of customers, Kubernetes customers, and what we've learned is that they're kind of two different things in many ways, and hopefully that comes across in my content. Let's start with the CPU side, the requests and limits. And I'm going to start with the basics. So when you launch a container in a pod, and it could be part of a replica set, it could be a part of a deployment, whatever it is, you need to specify on the CPU front requests and limits. How much CPU do I want to give to this thing? That it's like a reserved, but not really, but reserved. And then there's what's the limit? How much do I want to, what's the maximum I want this thing to get? And that is very hard to do. And I've done entire webcasts on this. And it's not that the engineers don't know what they're doing. You can know Kubernetes very well. You can be sitting at Grafana all day long. It's still very hard to set these values. And there's all kinds of reasons why that I won't get into. But one of the most obvious ones is that this could be replicated hundreds of times. And so I have to look at 200 curves to figure out what to set this to. So invariably, they're wrong. And it is their job of the app teams to make sure there's enough. So they tend to err on the high side, for CPU at least. And here's an example of an actual case where the orangey line is the request and the purple line is the limit. In this case, they're set to the same value, which is another problem. But this one's set to 2 CPUs, but this thing is barely using 3/4 of a CPU. So this is a case where the request is probably 2 or 3 times bigger than it needs to be. This does not need 2 CPUs to operate. But that's what we see an awful lot, this kind of thing where the request is higher than the utilization. Sometimes it's a lot higher than utilization. If I'm in my own context with my own app setting these values, this might make sense to me. But in the grand scheme of things, this generates a ton of cost. How it generates a cost is that if you have a cluster with node groups, and I'll just talk generically at a cluster level now, it will schedule those containers to run on the nodes based on that request value. So here's an example of a cluster where over time, 80 or 90% of the CPU resources are being allocated out to running containers, which is great. That's Kubernetes. That's its job, is to schedule those things. They'll launch new nodes when you run out of capacity in the current nodes. And generally, this thing is running along, giving out the resources pretty nicely. So again, the sum of all the requests is about 80% on average of the node capacity. But the node utilization, in this case, is down around 7%, peaking at under 20. So this is bad. This means that I'm not actually using any of those resources. I've over requested by a large margin the resources that I need. And I'll go back to, I mentioned overcommit earlier. The problem is that Kubernetes doesn't deal with virtual CPUs. These are real CPUs. If you ask for 2 CPUs, the scheduler says, okay, I'm going to earmark 2 CPUs for you on that node. When the node's out of CPUs, I move on to a new node. You can share with each other at runtime, but when it's scheduling, it does not overcommit. It just gives out the resources based on the request, and moves on to a new node. Now, in the VMware environment, to contrast this, if you saw this situation, you would just overcommit. You would use like an 8-to-1 overcommit, and then this box, the nodes would be running at 56% utilization average, which is pretty much what we would see in a VMware environment. You don't have that control in a Kubernetes environment. So when you ask for too much, it just directly hits the bottom line. You directly deploy too much capacity, and stranded capacity means high cost. That's the bad news here is we see a lot of environments, every environment we see, I analyze an awful lot of environments, everyone I see, there's a ton of waste in there because on the CPU front, they're just over requested. Now, if we step back and view this in scale, and this is a visualization that our product generates, and I'm not going to describe all the details of how it generates it. We have, again, other webcasts that go into detail on exactly what it's saying, but I want you to focus on the top left. So these are the CPU requests. The top right is memory requests, and then CPU limits and memory limits. And it's a visualization of how wrong you are across your containers. So this is an environment of about 11,000 containers. And again, I'll talk about the memory in a minute, but just focusing on the top left, what this is saying here is that around 1,800 of the containers are good. They're set pretty much correctly for CPU requests, but about 4,500 of them have over 5 times more CPU resources than they need. So even worse than that example I showed previously. So this is 500 and up. So thousands of containers are way, way too big. We have some that are way too small as well, and this could be a problem, and some that don't have values. That can be a problem if that gets too high, but in this case, clearly, there's a bias towards things being way too big. And this can generate, so from a FinOps perspective, this is a flashing light when you see that big yellow bar. Like I said, we see it everywhere. I think 100% of the environments I looked at have a big yellow bar because it's just the nature of the way people define the resources. When working in isolation, you err on the side of too big. And oftentimes it's way, way too big. And so the question becomes, well, how much does this cost? How much can I save here? And I won't give an overall number what we see. Every environment we see good numbers, but what I will do is show an example of one of these cases. So this is drilled down now. If I click on that link, you see the link above here, it says stranded CPU risk. So these are all drill downs to get to the details. You have risk of throttling, risk of stranding, risk of out of memory kills, etc. If I drill down, now this is the view into there showing me the line items that were handled. These are individual containers and their identity is being protected. But here we see a bunch of containers and all of their resource stats. Again, the UI shows this. The visualization is the easier way to see this, but you can see all the numbers. It's all API accessible. But if I highlight a couple of things, here's a couple of Tomcat servers that are requesting 4 CPUs each, but have a surplus based on our analytics of 3.96 CPUs. These things are about 100 times too big. So they're just not doing anything, but they each ask for 4 CPUs. So based on what I just mentioned, that is directly going to use up 8 CPUs. When the scheduler, when Kubernetes is scheduling, it will schedule 8 CPUs to these 2 web servers, basically, and then move on to a new node. And then that's not going to be utilized. And that causes that gap in the curve I showed. Now, that's interesting, but the third one down is possibly even more interesting. So this one's been given 11 CPUs, but 3.2 of those are surplus. So it's not as big a surplus as the other one. It's about 3 CPUs too big. And if I look at the bottom left, so that's the CPU utilization in millicores over 24 hours. And we're seeing here that it's sitting using around 8 on sustained, maybe peaking around 9, 9.5, but on sustained utilization is around 8 CPUs, but it's been given 11. So that's what it looks like. It doesn't even look egregious. It's not twice or 3 times too big. It's just 3 CPUs too big. But the interesting thing is this is replicated on average 128 times. This is a highly replicated launch configuration that's wrong. And napkin math on this says 128 times 3.22 is about 412 CPUs being wasted by one container, one config. It's a replica set. So there's a lot of containers, but there's one launch configuration, one Terraform file. You edit that line and change that number, and you'll save at least $173,000 a year. We quite often see an example like this in every environment we analyze, maybe multiple. There's usually some egregious outliers here where this one, it doesn't even look that bad when I look at it, but when you scale it out, it's bad. Interestingly, this is a very conservative estimate. It's even worse than this. Now, just a little subtlety here. This left curve is the busiest of those 128, which is what we base a lot of our decisions on. You can tune the analysis to do whatever you want, but we want to look at the busiest. So the busiest one is 3 CPU surplus. The average is even worse. It's 2 CPUs less. So on average, across 128, this thing's about 5 CPUs too big. And so the real savings is probably closer to $300,000. And of course, at discounts, maybe you're back to 2, but Anyway, just an example of, from a FinOps perspective, this is gold. This is the kind of stuff that you can isolate very quickly and go after and move the needle, theoretically. Now, let me kind of pull the brakes on that for a second. That is definitely the case if the nodes allow you to do that. So whether that has an effect, and this is where it starts to get complicated. So obviously that's too big. I can make it smaller. Yay, that's good. And some products just say that and do it. We go further than that because we say, well, will that actually move the needle or not? Will that make a difference? And the example I give is that if you have a node, if your node group is memory constrained, then reducing CPU doesn't do anything. It's an example of that looks like this. This is an actual example. And let me explain what you're looking at. This is a scale group analysis. So our Kubernetes analysis and our scale group analysis are linked together. So this the scale group analysis, for example, or the scale sets, and you understand the requests and limits, not just the utilization of the requests and limits. So here's a case where the scale group CPU utilization is averaging 1.6%. Very low. They're not using your CPU, but the requests are averaging 33% of the nodes. So again, this is even worse than any example I showed. This is real. This is the worst than anything I've shown so far. The requests are 20 times higher than they need to be. So there's a lot of room to move here. I can reduce the requests and get it more in line with the utilization, and I'm not stranding all this capacity. But the problem here is that the memory is 100%. So if I do that, it won't do anything. It won't change anything. I can't be on fewer nodes, and I can't run on smaller nodes or fewer nodes the way it is right now. If I do that right now, it's not going to save any money. So you can charge off and change that. And it probably doesn't make sense to change that when I showed in the previous slide. It may not do anything. But it will if I reconfigure the node type. In the CPU world, oftentimes if you make changes, it may have an impact in some node groups. It may not. But the main strategy we promote and we see out there is that if I do that, but then I change the node type to be memory optimized, then I will see some significant savings. In fact, in this example, I can right now change it to memory optimized. So I can do that before touching any containers and get a savings here. So from a scale group perspective, there's optimization I can do here just with the current state that will save about 30%. Even if this curve was higher, I can still save that. I just need to optimize some of the requests. So, and what that looks like, and it's what we call realizable gains. So there's actions you can take, but before rushing out and just taking actions, understanding that they're going to make a difference or not, and whether they'll move the needle or not. So in this case, this environment, the good news is I can actually move the needle without touching any containers. But if I optimize a few more containers, I can get that higher and higher by changing to a memory optimized node. And I'll show that in a picture so it's easier to understand. So if I analyze, the Tetris blocks are the container utilization and the dotted lines are the requests and the orange squares are the nodes, then what I do is I get these utilization values, I analyze them, and I come up with new requests, which for CPU are quite often lower. So I bring those down. What happens is then when they get redeployed, the containers then get lower CPU requests. Now, metaphorically here, vertically is the CPU and horizontally is the memory, picture if you will. So I lowered the CPU, but I didn't touch the memory. So I still need all the same number of nodes, but I can run on different nodes now. So I can say, okay, now move to memory optimized, save 30%. I readjust the nodes with the right CPU to memory ratio for what I'm running. And so in the CPU world, you may have some quick hits right away, but quite often what you want to do is bring down the CPU and then just reconfigure the nodes. We do all that automatically because this is all linked in the analysis. So as you downsize CPU requests, we will automatically start recommending different node types in the scale groups, and that happens automatically. So from a CPU perspective, I'll talk about memory for a few minutes, but the CPU perspective, there's tons of waste. You can unlock it, but it's not just a matter of, it's not like just saying downsize the web or the cloud instance to a medium. It's not that simple. You need to change the request and then readjust the scale groups, and then it all starts costing a lot less. So huge potential. It just needs to be done correctly and in the proper order. Now, I'll talk about memory for a few minutes, so don't run too long here. Memory is, if I use the same diagram but talk about memory, same problem, harder to get right. In this case, here's an example. This is a real example where the memory was 1 gig, but the container is using between 2 and 3 gigs. So it's too low in this case. And in memory, we see both too high and too low. It's not like CPU where everything's kind of way too high. It's a mix, and it really depends on the environment. In this case, the limit is also too low. If you're touching your limit like that, that's bad news. FinOps, from a FinOps perspective, it's not going to affect cost, but the SREs really want to know about that. So if you're analyzing the environment, you see this situation, which we automatically detect, you got another problem. This thing might be getting killed. But from a cost perspective, this is complicated because this one's actually too small. So this one, I need to add more resources to it, which might incur more cost. And if I go back to this kind of 11,000 system view, the visualization I think these are all the OpenShift containers running in Azure. That's what we're looking at here. 11,000 in a certain environment. So we saw that yellow bar for CPU. Memory is all over the place. So about 1,000 containers have a fifth of the memory they need, which could be a big risk point because if you have that memory kills, but thousands are also way too big. And it's the spread, it makes it very complicated. This might have a net surplus of memory. It might not. Even more operationally, this thing's going to be a mess. And we see this again and again. So there might be cost savings here. Are there savings? Is that savings? Well, it depends. And typically, yes, but you can't go after the yellow until you fix the red. And you can't downsize things until you upsize things. And there's a very specific reason for that. Here's an example. Let's go back to the nodes. This is a node group under a container environment of 72 nodes, workers, the big environment. And this is the average and peak memory utilization of those nodes. And you see some of them are 18%, some of them are 34%, some of them are 98%. So it's all over the place. There is spare capacity here. But the problem is, if I sort this by the peak memory, a lot of the busiest nodes are basically hitting the roof. Anytime we see 70, 97, 98, 99, this thing is basically saturated. It's got trouble. And so, for example, this top one, it is absolutely hitting the roof after 6 p.m. in this case, on this day. This is causing out of memory kills. In this environment, it was absolutely causing out of memory kills. This node was running out of memory, whereas the lowest node in the list wasn't even hitting 20%. And again, so I don't recall the average in this environment. There was a lot of spare memory, but you can't use it because of this imbalance. It's a mess. Because of that spread in that histogram I showed, Kubernetes just doesn't know what to do. You're giving it garbage. It just puts stuff where it thinks it should go based on the request. They don't match utilization. Some nodes saturate and some don't. So even though I have stranded capacity and there's probably quite a bit of cost saving in this environment from a memory perspective, I'm not going to touch it. I don't want to add one more workload to this environment, one more container until I fix this because it's already straining under the load because it's misconfigured. So there is cost savings, but it's a mess. If I look at this from that Tetris point of view, the reason this happens is because if I run a workload that uses quite a bit of memory, but I don't ask for enough, Kubernetes doesn't see the utilization. It just sees the free space based on requests. It'll keep scheduling these things onto a node until it blows up the node. That's exactly what that previous thing was showing. At the same time, and in the same node group, if I have things that are over-configured, I'm using so much memory, but I'm asking for way more than I need, Kubernetes says, well, I see some free space on this node, so I'm going to schedule one more of those, and then I'm going to move on to the new node. But in practice, it's only using a fraction of the node, and it happens in the same cluster and the same node group. That's exactly what I showed in the previous screen. So theoretically speaking, Kubernetes doesn't know what to do if you give it garbage, and even if there's a lot of spare, these operational issues mean you want to fix the red before you fix the yellow. And interestingly, what we see quite a bit is that if you happen to get lucky and these schedule together, they help each other. So if I have one container where I ask for 1 gig too much of memory, and I have another one where I ask for 1 gig too little, and they end up on the same node, they can use each other's memory. Kubernetes doesn't stop you unless you set a limit on it. They will use each other's memory at runtime. So we actually see cases where they're helping each other. Well, one is keeping the other from getting killed. Again, it's not just getting lucky. Statistically happens quite a bit in these environments. So you can have overstacked nodes. You can have nodes that look okay, but for the wrong reason. And you can have understacked nodes. And so the bottom line is the red needs to be tackled first. So even if there's a lot of cost saving opportunity, you need to upsize things first. If you downsize first, if you take that yellow one in the middle and make it smaller, Kubernetes might start shoving more work on this node, and then you'll hit the roof and it'll blow up. So again, lots of cost savings, but the way you approach it is nuanced, especially for memory. So of course, the ideal thing, you go after the risks first, is often what we see. If you're really into automation and you want to just go for it, and I'll show you a customer that does this in a second, you just do it all at once. So if I just say, let's take that, analyze the CPU and memory requests all together, upward and downward, just fix it all, reschedule. When they rerun again, the dotted lines will match the workloads better. If you do everything at once and get it right, quite often Kubernetes will just run on fewer nodes anyway, because it's doing better bin packing. So we see cases where you can just see it's elastic in the fact that if I just optimize these things, it'll run on less infrastructure without doing anything to the nodes. Of course, then you sweep in and optimize the nodes and make an even bigger difference. So I just saved a third of my cost by letting it run on fewer nodes. I can save another 30% by going to memory optimized. We see some environments that are on Cs, and you can sometimes go 2 hops and save a ton. And while I'm at it, why don't I put that on the latest thing, which is what our cloud analysis automatically does. So the cloud analysis is kind of doing the left-hand side, container analysis is the right, and they work together. And that R7 may not be cheaper, but it's probably a bit faster. It probably works better. And so that's kind of the end story if you do everything we say. And then you'll save a ton of money and it'll work a lot better. All those out of memory kills will go away. Let me just close off by saying what good looks like. This is an example of a customer that does it all at once, where this is actually an on-prem OpenShift environment. So that everything I've been describing applies to both on-prem and the cloud. The main difference between on-prem is that you have a lot of lead time for procurement. So it tends to have more of a capacity management, capacity planning angle, but the optimization is the same. And these guys, they hit our API dynamically every time in this case, an OpenShift container is deployed. They automatically bake the answers into the OpenShift templates and put them back into the pipeline. So every time they deploy a new container, it's optimal. And in doing so, this is what they look like. This is what good looks like. There's no gray. Everything has a value. There's not a lot of yellow and not a lot of red. There's a bit, and that's really because we don't make big changes. The policy says don't make too big a change at once. So we tend to not go crazy and work towards the optimal solution. So it might take multiple hops. There might still be some red and yellow in the maps, but this is a really great case. The environment's calm. There's no kills or fewer kills for sure. And they cut their new infrastructure spend in half doing this. So big FinOps win, but also a big operational win. There's a case study on our website for this, and it's going to be automated. And that's another topic for a different webcast. But it's all done at once. And I guess that's back to my kind of walk down memory lane. I think that the having enough and not having too much in the container world kind of needs to be done together. You can't just look at it in isolation, but with the right analytics, you can do it all at once. You can understand how to prioritize and get big gains from a cost perspective, but also big operational gains. And I mentioned I analyze an awful lot of environments and they all have these problems. Like all of them. Every one I've looked at has the big yellow bar and has a spread on the memory. And so when you see that picture, it's almost like an MRI. You can tell pretty quickly what's going on. So this is across the board, even the most sophisticated customers and environments. There is huge opportunity here if this is properly analyzed.
A good segue, Andrew, to a couple of the summary slides. You use the term realizable gains. A great way to see what's realizable gain-wise in an environment is to do a trial with us. Some of the specifics here, there's a QR code if you want to link direct to the trial request. No strings attached, very little downside. We get the data through Prometheus. We will show you both the health and risk reduction opportunities that generally platform owners want to see, which is in Andrew's content, getting rid of the red, the risk, so that you can then go after the cost and efficiency opportunities that, as he says, are lurking in most environments. So encourage you, it's not a hard sell. It's an opportunity to see what's happening and potentially realizable gain-wise in environments. In the interest of time, Andrew, I'll just hit on one question that was logged that's very germane to your topic, which was how Densify deals with quality of service-based settings in Kubernetes.
It's a good question. And I think I might have touched on one of our other webinars on optimization. So we do support that. It's on the policy settings. You can set what Kubernetes calls overcommit, which is what I've been showing, where the request and limit are different values. So limit is higher than request. If you do that, you get higher efficiency. If you set request equal to limit, especially for memory, we support that as well. It does tend to make the cost go up because you need to set the limit above the busiest replica. And so if I have to set the request to that same value and they're both above the peak of the busiest replica, I will end up having higher request values. So one study we did in our customers, it was a 50% increase in the request values to make sure we lasso get all the right peaks. But it is theoretically safer to run that way. So some customers run that way, some don't. Some people advocate that, some don't. We don't really take a strong opinion on it. We can analyze either way. It's a policy setting. But again, it's interesting to see if you do A/B test, if you kind of do a what if with that policy, you can see what the cost increase is of running guaranteed quality of service versus overcommit.
We will be at KubeCon in Salt Lake City in November. Happy to see you and talk to you and demonstrate. And we do have another Kubernetes related or focused webinar on September 19th, looking at auto scaling and optimization and the difference between the two, because they are sometimes confused. So welcome you in that event as well. Thanks, Andrew, for the time today.